Okay, so if we're all back, welcome, I guess, to the second lecture of today. I have set all the kind of counts back to 0, so new day, new opportunities. So before we kind of start, and what I want to do today is to actually discuss key exchange, let's maybe briefly remind ourselves of the most important things that we had learned yesterday. Okay. So the first thing that we had talked about yesterday is how to what does it mean to be random, and when do we say that we've successfully generated some random bits. So let's say that I want to generate m random bits, and here actually I've called them km in anticipation of the key that we're going to generate today. Okay. And so yesterday I had said that, well, the ideal beautiful scenario of producing some m random bits would be that the bits are uniform. Okay, so every bit string is equally likely, and also it is uncorrelated from any environment. Okay. So the second thing that we had discussed that I want to remind you of is this trace distance. Because I guess if we kind of build a machine or we build a device that produces random numbers, this beautiful utopian ideal scenario can never be achieved. Okay? In fact, in any practical situation, we can only do so approximately. Okay? Namely, we can only make sure that the real state produced by our device, we can only hope that it's close to this utopian ideal world, where close is specified in terms of the trace distance up to some accuracy parameter, epsilon. So can someone maybe remind me why the trace distance was so interesting to us? Do you remember? Maybe I can point to this list. Yes?
Because it tells you how well you can separate out radial and radial powers.
Okay. So remember that yesterday I had said this distance is important, because if this distance is small, then there exists no physical process that can tell the difference between the ideal and the real scenario. And if you don't want to think about a physical process, you can also think about an algorithm or a protocol that is going to use these random coins. If this protocol or algorithm would behave very differently, depending on whether I give it the ideal or the real state, okay, then I could tell the difference between ideal and real. That cannot be if the trace distance is very close. Okay? So this is kind of why the trace distance is very important, because it has this operational meaning of giving essentially kind of the same behavior if I'm close in the trace distance. And unfortunately, I remember you from yesterday, Renate will be completely pleased with this. I guess I'm afraid the ETH is already 1 point ahead today. So the second thing that we had discussed yesterday was the min entropy. Okay. And the min entropy kind of told us of some kind of string, x, told us how difficult it is to guess the string. Okay. Because kind of the min entropy is just minus the log of the probability that kind of if I have some side information E, some information that I've maybe collected or that I have about the device, that might help me to guess x. Can someone remind me why the min entropy was especially important? Like, why would I not consider the Shannon entropy, for example? Yes?
It also gives me a measure of how uniform my distribution is.
Okay. So it tells me something about how uniform the distribution is, how flat it is, in fact, because this is like the largest peak of the distribution. Any other suggestions of what the min entropy is important? Yes?
Well, mathematically you can connect it to D, right? And you have the formula that connects P guess H min to D.
That's right. Okay, so like if kind of this had kind of just two options, okay? One way to write this guessing probability, if this is some kind of quantum information, it means that basically you have a state that might somehow depend on the string, and you want to distinguish these different states.
It also gives a bound on how many bits I can extract out of a string.
Okay, very good. Okay. Actually, I guess I have to make some stripes. I think there's like one here. Is that right? Okay, very good. Okay, so this was a very good point. Okay, so the min entropy was very important because it kind of tells us something about how many perfectly random bits, or almost perfectly random bits, we can actually extract from some source. Okay? So we had said yesterday that if I have some kind of source of randomness that produces n bits, okay, according to some distribution, then we might ask, so how many almost perfectly random bits can we obtain from that? And we had seen that there's a simple argument that we can never hope to get more than kind of the amount bits out than the mean entropy. Okay, so the amount of bits is certainly not larger than the mean entropy, and this can also be attained. And actually, I'm going to erase this, but I guess the number of bits that come out, we saw scales as the mean entropy minus the log, or 2 times the log, of this accuracy. Okay? So the accuracy means that kind of how close should my output bits be to this ideal world. Okay. So yesterday kind of we had talked about what it means that an extractor is a strong extractor, because there was a very valid point, an objection raised by, I think you actually, that, well, you know, if I start with some kind of random string x, and I give you some random seed s, some perfectly random numbers with which you can choose a function, well, it might not be so surprising that some random bits come out, because after all, we started with some random seed, and we produced some random bits at the end. It's not particularly surprising. Okay. So kind of the nice thing is that kind of what it means to be a strong extractor is that the bits that are generated, so I'm calling them here k, are independent of both E as well as the seed used to produce them. Okay. Can someone actually remind me why we had used this random seed? Like why do we need to bother about such a seed? Why can I not, for example, just extract from, I don't know, a string of n bits if I have a lot of min entropy? Yes?
We discussed that if you don't know anything about a bias of our random number generator, we cannot use extractor to increase, to extract anything.
Okay, very good. So yesterday we had seen that if I have a device and the only thing that I know about this device, the source of randomness, is the min entropy, then there exists no kind of function that gives me some random numbers. Or in the other way around, if I know that kind of you're going to use a particular extraction function, and I'm going to now sell you a source, okay, I can construct a source, I can find a probability distribution over strings such that, well, it has a lot of min entropy, yet I can perfectly predict what your machine will generate after you apply this extractor function. So in other words, kind of deterministic extraction was impossible, but we can do so using some random seed. Okay. So what I want to do today, and I guess we can launch into this, is to make the situation slightly more complicated. Okay. And I want to introduce you to, I guess, the kind of world of cryptographers where there's kind of eavesdroppers, okay? So today we'll think about an eavesdropper, and this eavesdropper is called Eve. Okay. And the whole objective of this eavesdropper until the end of the lecture will be to listen in to our communication. Okay. This is a very curious eavesdropper. She wants to know everything. And the bad news is that also Eve is all-powerful. Eve has long figured out how to make a quantum computer. She has an arbitrarily large quantum memory in her basement. And kind of her only goal in life, in fact, is to read the communication between Alice and Bob. Okay. 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 So to remind you what we had done yesterday we had considered, you can think that what we had done yesterday is we had considered one party, Alice, and what Alice wanted to do is to produce some random bits. Okay? So this is what we had done yesterday. Alice's goal was to produce some random bits, k1 up to km. Okay, so I'll call this k Alice. This is like what Alice produces. Let me put here Alice. And what we had wanted is this situation here. Okay? So we were just concerned that these bits k here are uniform and independent of anything else, okay? Any environment. In particular, you should be thinking here that this system E, okay, this is why I had called it E yesterday, is held by this eavesdropper. Okay, so for this talk, you should be thinking that Eve kind of has rho E. And if we're wanting to make random numbers, we were concerned with that this here is uniform and uncorrelated from Eve. Okay. And so in other words, this means that Eve does not know the outcome of this random process. Eve does not know which bits Alice has produced. Okay. So when you go to talks about crypto, people will often say something like, the eavesdropper does not know something, or Eve will be ignorant about the key. Okay. So if cryptographers say Eve does not know something, they actually mean that the state of kind of whatever that something is, here the key, and whatever Eve has looks like this. Okay, so if a cryptographer says Eve does not know the key, they mean that the key is uniform and Eve is uncorrelated from the key. So today we'll make this slightly more complicated because I don't just want Alice to produce some random numbers that Eve is ignorant about, but I want that in fact we can kind of produce the same random numbers at two places. Okay? So our objective will be to create, say this, some key bits for Bob, call this KB. And in fact, kind of the crucial demand that we're going to make is that these here are the same as the ones that Alice produces. Okay, so maybe let me put here K. Okay. Not this to be permanent. So note that the fact that the key should be the same is of course very important. Okay? If I were to just say, well, the objective of kind of making a key is to produce something that is uniform and kind of uncorrelated from Eve, well, Alice could flip some random coins in her lab, Bob could flip some random coins in his lab, and well, as long as Eve has no access to these labs, maybe they succeed. Okay? So what makes this difficult is that we want them to be the same. Okay? So the fact that they're the same means that we can call it an encryption key, and Alice and Bob can later use it in some standard encryption algorithm to protect their information. So my question is kind of how we're going to achieve this. And the first thing that actually I want to consider, of course, there needs to be some kind of way for Alice and Bob to communicate, is what happens if Alice and Bob actually already have a private channel. So if I say a private channel, you can think that there's a wire kind of going from Alice to Bob. And we can be sure that whatever kind of bits come across, Eve cannot read these bits. Okay? So Eve has, of course, physical access maybe to this wire, like it's running actually through Eve's lab. But Eve cannot read the bits on the wire. Now I'm asking you, can we use this kind of private channel to produce such a key? And my demand will be that kind of whatever Alice has will be the same as what Bob has. Yes?
Well, if it's truly private, we can just send the key.
Okay. So indeed, so like one thing that we could do is we could just send this key across. Okay, it's truly private. Okay, so Eve can certainly not read the key. But my question is, can we make sure that in this case, in fact, the key produced by Bob is the same as the one from Alice? Yes?
I think she might still do something with the wire and this changes the key. So
Okay. Okay, so very good. So Eve might actually do something to this wire. Okay? So even though kind of Eve might not just intercept these messages, she might kind of actively try to inject some new messages into this wire. And her only objective will be that Bob has a different key. Okay? So for this reason, in fact, an important resource that we're going to use today is I'm going to assume that Alice and Bob are connected by a classical authenticated channel. So we're going to give Alice and Bob a resource. We're going to assume that there's a classical authenticated channel. So this an authenticated channel means that kind of if Bob listens at the output of this channel, he can be sure that whatever bits roll out of there are actually sent by Alice and not maybe by Eve. Okay. So you might be thinking kind of where does such a classical authenticated channel actually come from? Okay. So it's possible to generate such a classical authenticated channel if Alice and Bob share a little bit of key ahead of time. So they have some kind of tiny amount of key that they shared somewhere in the distant past, and they can use this to produce a classical authenticated channel. Okay. So of course I want to make this slightly more interesting, so I'm going to give you this authenticated channel, but now it's no longer private. Okay. So this is not so cool, because I mean we can try and send this key across now, but certainly your strategy doesn't work anymore because Eve might listen to it. So I want to now assume that there's another channel connecting Alice and Bob, and before we talk about quantum, I actually want to make this a very simple channel. Okay? Namely, it's going to be a classical channel that connects Alice and Bob, but Eve cannot listen to it perfectly. Okay? I don't know, maybe Alice and Bob are actually talking in the same room, and Eve is listening on the door. So whenever a bit comes across, I'm going to say that Eve can kind of obtain this bit with some probability p. Okay. And also here is somewhere Eve, okay, so he's trying to listen in. And every time a bit comes across, she can kind of listen to this with some probability p. I don't know, we can put something, say probability like a fourth maybe. Okay. So Alice sends a bit to Bob, and with probability p, it's intercepted by Eve. Okay, so Eve knows when she got the bit, and that she's successful with probability a quarter. So now my question to you is, do we have some idea of how we might still produce a key from this scenario? Okay. So previously we had just sent the classical key over the wire, but maybe we can't quite do this anymore, because certainly Eve will not be completely uncorrelated. Every bit is known to her with probability a quarter. Yes?
If we accept that there will be a certain probability of P being able to guess, like we say we're fine if there is only 1% chance of P being able to guess, then we can have we can decide beforehand which bits are going to be our key and send a much larger number.
Okay.
So Eve won't know whether what she's getting is part of the key or not.
Okay, so there's a very important idea here, namely that instead of just sending these m precious key bits that we want to generate, we might actually first send a much larger string. Okay? So let's kind of think about this. So we'll kind of construct a protocol. And the first step of our protocol will be actually that Alice is going to generate a much longer string. I will call this x1 up to xn. Okay, so n is larger than m. Okay. And maybe we can send these bits over the wire from Alice to Bob. So what's going to happen, of course, is that every time like one of our bits travels across, Eve will intercept this with probability p. So of course it will not be that Eve is completely uncorrelated from this x, but there will be some probability that Eve is going to guess every bit of the key. Okay. So can someone tell me actually what is the probability that Eve manages to guess just one of the bits? I don't know, let me say first bit maybe.
Just a guess would be 1 over 2.
Huh?
If it was just a guess, it would be 1 over 2.
Okay, so if it was just a random guess, it would be 1 over 2. That's right. But note that every time a bit kind of travels over our wire, with probability a quarter, Eve manages to intercept it. So with probability p, Eve will get the bit for sure. Okay? Then she just outputs that bit as her guess. But of course, there might be some probability that she fails in her interception. Okay? And in this case, with probability half, she might still guess the bit. Okay. Yes?
So does Eve know when she got it right or not?
Ah, that's right. Yeah. So like I said that earlier, indeed, Eve knows when she gets the bit. Okay. So you can think that Eve gets a kind of signal saying, "I've successfully intercepted the bit, and this is the bit." And this happens with probability a quarter. Yeah.
And also she knows when she missed it, right?
That's right. Yeah. 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 So you can think that kind of what Eve is going to do, if she sees that she's successful, which happens with probability p, then she just outputs this as her guess. In fact, it's correct. And with probability 1 minus p, she's going to fail, and she knows that she failed. And then she's just going to make a random guess. She's going to flip a coin, and this will be her guess for the bit. Okay. Okay, very good. So we do this many times, like n times. And my question to you is, can Alice and Bob now still make a key from this scenario? Yes?
Don't we have exactly the case we discussed yesterday that we have now H-min, which is not anymore 1/2 or whatever for the bit length, but that thing for the power bank, and we just use extractors.
Okay, very good. Excellent. Okay. So we know there's something about this guessing probability. So we know something about the min entropy of this string. Okay, so let me just call the string again xn. And we know something about its min entropy. Namely, we know that Eve can guess every bit with this probability. So there was a claim here that the min entropy of this entire string given E. So note that this happens for every bit, okay? So kind of the probability of guessing the entire string is like this to the power n. It's independent for every round. To the n, okay? Which is n times this. So indeed, like you remembered from yesterday, that there's this kind of magical thing called the extractor. Okay? So we are now in a situation where even though we have not reached this beautiful utopia of having kind of Eve being completely uncorrelated, we know something about her min entropy. Okay? So what we're going to do now is we're going to extract. Okay? So what this means is that Alice kind of chooses a seed. So what I mean with Alice chooses a seed, Alice has some kind of randomness. She has a randomness generation device. She's going to generate like R bits of seed, and she uses them to pick some function. Okay. So yesterday I said, for example, 2 universal hash functions are good, but there's many possible extractors that we might want to apply. Okay. So Alice chooses as the seed, and what she's going to do is she's going to take the string x and extract. Okay? So that gives us a much shorter key. And as we had said yesterday, well, if this is an extractor, then I can be sure that if the min entropy is reasonably large, okay, then in fact the output of this will be close to uniform and uncorrelated from Eve. And this is the case as long as we don't want to get more bits out than the amount of min entropy that we started with. Yes?
Did you assume that Alice and Bob, they know probability, right, of Eve? I mean, like, in principle, it could be that they don't know about Eve anything, and they didn't know probability, so that's why you don't know mean entropy. That's why you don't know what exactly, how much of information can you extract.
Okay, so that's I'll get to it in a second. So this is a very good point, because as you have correctly kind of discovered, that I had to know something here. Okay, so I can only say something about this entropy if I'm going to promise you, in this case I promise you, that somehow we know, I don't know why, but somehow we know something about Eve. Namely, we know that this probability of interception is, say, a quarter. Okay. So in general, of course, we don't know that. Okay? And this is kind of where quantum will come in very helpful for us, because then we don't know about it, but we can test for it. Yes?
So what I wanted to point out is that you actually wrote down that the P guess is conditioned on E.
Yes. I guess I have like written E here, so you can think that like for every bit, like E is also generating some kind of string here, E1 up to.
So this is information about E which Alice and Bob actually do not know yet.
That's right. So like note that Alice and Bob, of course, don't quite know what Eve is going to do. Okay? The only thing that I've given you here is a guarantee about how much kind of interception abilities Eve has on our channel. Namely, I just made you a promise, namely that, say, I promise you that this channel has the property that Eve cannot perfectly intercept, but she can intercept with probability 1/4. Of course, you might ask why, okay? I just wanted to make an assumption first to kind of see what we're going to do. Yes?
What if Eve just blocks all lines between Alice and Bob?
If she did what?
Block all lines between Alice and Bob.
Okay.
So what happened here?
Okay. So like that's a very good point, because like the question is, what happens if kind of Eve kind of prevents Alice and Bob from communicating at all? Okay. So she might perform some kind of denial of service attack that kind of makes it impossible for Alice and Bob to talk to each other. So there's no kind of way of kind of communicating, or there's no kind of cryptographic system that can protect you from such an attack if Eve is all powerful. Like there's some methods in classical cryptography actually that to prevent a denial of service attack, I make it such that Eve has to solve all kinds of computationally hard problems in order to execute this denial of service attack. But this is not going to do here, because remember that Eve is in fact all-powerful. She has a quantum computer in her basement. She can solve any problem in an instant. So we cannot do anything like that here. Yes?
So is it now just a problem for Alice and Bob to use the same seed?
Aha, okay. Yes, so there's a worry here, okay, because like Alice had chosen the seed, okay, and she produces this outcome. But of course, we want that Bob's key is going to be the same. Okay. So let me maybe on this side write what happens to Bob at this stage. Okay, so at this stage, kind of Bob. Actually, can you read the blue? Is blue good? Yes. Okay. So Bob certainly has x1 up to xn, but he does not yet know the seed. Okay. What are we going to do?
Well, he can use any seed.
We can have a database. In the beginning, we can have database of the seeds which we are going to use. Because anyway, even if Eve knows this data, this instructor, she's not going to predict your result. Yeah.
Okay, so there's kind of two different points here, and let me kind of address them separately. So Alberto has said, Alberto, excellent, has said that, okay, maybe Bob doesn't need to know the seed, and I want to kind of emphasize that he does, okay? So remember that what we had used the seed for is to choose at random some hash function. Okay. So if Alice and Bob have the same hash function, like I apply the same function to this n-bit string, then in fact they will produce the same outcome. Just because they started with the same string, I apply the same function, the same thing will come out. Yes?
Do we assume that E has this list of hash functions too?
Yes. In fact, okay. So there's a question, kind of, does Eve know the set of hash functions? And the answer to this is yes. Okay. So in crypto, I was going to say a bit more about this in a moment, it is always assumed that Eve knows the entire protocol. Okay. So not only does Eve have a quantum computer and an arbitrarily large quantum memory, she knows precisely the protocol that Alice and Bob are going to execute. She knows the hash function, she knows all of this, like lists 1 up to 2. Okay. So the only thing that Eve cannot do is kind of peek inside Alice's and Bob's lab. Okay? So it's always assumed in kind of crypto that there is at least some portion of the world that Eve does not have access to, which is kind of the inside of Alice's and Bob's lab. So this means that even though she knows this protocol, she does not quite know what are these kind of bits generated here, because Alice is going to generate an n-bit long string, and then she puts every single one on the wire. Okay? So this Eve cannot see. She can only look at what comes out of Alice and Bob's lab. Yes?
If we just send seed as well, and Eve does not have the perfect same seed, then the output, if she uses an extractor, should be uncorrelated to the output of the other.
Okay. So there were kind of 2 suggestions here, actually, regarding the seed. One of them might be, let's kind of just send the seed here, and we can be sure that Eve also does not learn the seed perfectly. Okay. So we could be doing this, but kind of going back to your question, or like your kind of comment, is that we don't actually even have to worry about that. So remember from last time that these extractors, or strong extractors, had this property that even if I give you the seed S, nevertheless, the output will be uniform and uncorrelated. Okay. So what this means is you can think that E had originally held this register E. Okay. So say that if Alice now sends S to Bob, okay, and she might as well use a kind of public channel to do that, then even if Eve learns S, so even if Eve has E and S, nevertheless the output will be uniform and uncorrelated. So basically in our protocol, Alice can pick a random hash function herself. She applies it to get Ka, and then she's going to tell Bob, okay, Bob, I have applied this hash function. This was my seed. And Bob can then apply the same hash function. Okay, so what Bob does at this point, okay, put here. So at this point, let me maybe. So Bob learns the seed S, which means that he can now also compute KB. Okay, very good. We have exchanged a key, yes?
So, perhaps you said that, but is it true that Eve cannot get better than mere guessing by knowing the bits she has from this case, from the X string, and by knowing the seed, or is it just too hard?
Okay, so that's a good point here. Like, is it maybe true that is there some kind of difficulty assumption that maybe if Eve would be even more powerful, she could kind of come up with, I don't know, a ways to still break this, in the sense that she could kind of, it would not be enough to know this min entropy, and then if we send the seed and we apply the extractor, she would still be able to figure out what is Ka. Okay. So the important part here is that if we can somehow bound the min entropy of Eve, Okay, so somehow we have some guarantee, in this case by my kind of trivial example, where we're just sure that she only has a certain probability to intercept. If we manage to bound this min entropy, then in fact even an all-powerful Eve, okay, she has a quantum computer, she snaps her fingers, every problem is immediately solved. She can solve NP-hard problems immediately. Even then, Eve cannot have any advantage in getting this key. So this is quite cool. So we can kind of see that these kind of techniques that we've learned here, like this kind of the notion of the min entropy and this extractor, are very powerful. Because basically, whenever we can get and establish some kind of guarantee on this min entropy, we are kind of in business. So what I want to do now is I want to consider a slightly different scenario. It's again a toy scenario. I'm going to make an assumption. Okay? And I'm going to assume now actually a limitation on Eve. Okay? Just want to give you one more example where we might know something about this min entropy. So we have here Eve. And let me for the moment just make an additional assumption. Like we're later not going to assume that because she's going to be all powerful. But let me for the moment assume that she can only store a small number of qubits. Okay. Let's assume that kind of Eve somehow, I don't know, maybe it's the end of the day. Actually, we are before lunch, so I don't know. Maybe Eve is also not so completely fresh. Okay. Let's assume for the moment that Eve can only store k qubits. And my question to you is, can we still establish some kind of guarantee about this min entropy? Yes?
Well, we know for sure that she hasn't the difference between n and k qubits. So the probability that she guesses right is 2 through the whatever the difference is, n minus k.
Okay, so like Eve has a kind of limited memory size. So certainly she cannot kind of store all of this information. Okay, so she can maybe select to keep a few rounds. But at some point, kind of, yes?
But she is powerful, right? She can perform calculations in the continuous way. And Alice and Bob, they have some time to transfer. That's why she can perform some I don't know, some calculations, let's say dynamically, no?
Okay, so like, let's say that in fact, let's consider the following scenario. In fact, Alice and Bob are Alice is going to send all of these n bits at the same time to Bob. Okay? Let's actually give even more power to Eve. And on all of these n bits, she can kind of look at them at the same time, perform some arbitrary computation. I don't know what she does, but something. But at the end of the day, she can only store k bits. Okay? Yes?
So we've seen this min entropy of x depending on E is bound by the min entropy of x
Very good.
minus the log of the dimension of
Okay.
I think.
Okay, so very good. Yesterday, like we had discovered one of these properties of this min entropy, namely the min entropy of x given E is at least as large as the min entropy of x minus the dimension of E. And I had written the dimension of the E in this way. Okay. So if I can store k qubits, then the dimension of this is 2 to the k. Very proud. Okay. Okay, so excellent. Okay. So in this case, we actually know something about this, okay? Because in our case here, for this example, this here is just k. Okay. Can someone tell me what this is if Alice chooses this string randomly? Guess you had already.
Yeah, that's n.
Yeah, okay. So this is just n. Okay. So this means that the min entropy is at least n minus k. So we kind of see that as long as, yes?
This would not require that Alice has more than k bits, right?
Okay.
So if Alice is less than that?
That's right, yeah. Okay, so we already see that if we kind of want to run the same protocol again, where we kind of take your suggestion of kind of making a very long string that we kind of send across, and then we kind of pick a seed and we extract, then this can of course only work if we now make n bigger than k. Okay. So you can only hope to get some key out if this n is much bigger than this k. Yes?
I have a question for if Eve has 1 qubit, I mean, she could store all the information, right, in the precision of your face. You cannot read it out anymore. She could store it.
Okay, so there's a good point up here, like, or kind of a good question, namely, like, why can Eve not take all of these n bits, okay, and then code them somehow into the state of 1 qubit? Okay. Like maybe because like a qubit, I mean, it has some continuous degrees of freedom. I can like rotate it around, and I can kind of, I don't know, with arbitrary precision, kind of put my n bits in there. You've already pointed out that Eve cannot get them back out. Okay. So Eve cannot kind of, she can do this encoding, but she cannot read back these n bits. Do we agree on that? Or? Yes. Okay. So note that the guessing probability is determined by, well, Eve now takes her qubit, okay, and she can perform some measurement on that, and we're interested in whether this measurement correctly reproduces the string x. Okay. So this guessing probability kind of really captures Eve's ability to kind of produce x given whatever information she collected. So in your case, kind of if she takes this n bits and she encodes it into the rotation, like in the block sphere somewhere, then she cannot get back out, meaning that she cannot guess x. Does that address your question?
But if you now, for example, make the extraction as well on with that 1 qubit or your k qubit, and then you have a lower number of bits inside safe, right?
Mm-hmm. Okay, so there's a question now, because I guess you're asking, well, actually Eve does not really need to produce the all x, okay? Because actually in the end she just wants to know k. So the point about privacy amplification is that, in fact, we don't need to think about this at all. We don't need to think about what are the ways that Eve could possibly obtain this k. We are guaranteed by kind of the kind of proofs of randomness extraction or privacy amplification that if we know that the min entropy is large, then even if we kind of choose a random extractor, we apply it to x to get some kind of key, nevertheless, Eve will be kind of, the kind of key will be uniform and uncorrelated from both Eve and also the seed. So even if Eve knows the seed, she will be very close to being uncorrelated. Okay. Yeah, so that's a very good point. It's very kind of good to understand that, because we've kind of made our life a bit simpler here. Okay. We don't need to think about this k, we just need to think about the min entropy, and we want to make it large. Yes?
Is it necessary to know k to be, for example, to decode your algorithm? And like, maybe there is some way when you have this qubit vector and then you use some quantum algorithm just to decode message, you are not able to reproduce your k, but you will be able to read the message.
Okay. So there's like another question is, I guess your question goes to the question, what are we later going to use this key for? Is that your question?
Well, my question is, if it's powerful, as you said, we consider she has quantum, some, let's say, very powerful technology which you don't know about. And if she is going to store your key in the vector of your qubit, for example, which is continuous and so on, she cannot extract k. But if she's going, maybe there are some algorithms how she can use this vector to produce some information which she wants to know. Okay. But so she cannot reproduce k.
Okay. So there's kind of a point which I guess relates to the question what happens afterwards, right? Yeah, so Eve might store something, and then we're going to produce this k, and then later we might want to do something with it. Yes. And then maybe Eve can still find something out about how we're going to use it later. Okay. So for this reason, it is very important kind of that we wanted this approximation to hold in terms of the trace distance. Okay? And this trace distance actually does not just look at K or what Alice has, but involves Eve's register. So let me now assume that there would be some attack by Eve or something that Alice and Bob are later going to do, okay? Where this would indeed make a difference. Okay? So somehow Eve gains some advantage from the fact that she has done this encoding, and maybe later, like, I don't know, uses this encoding to find out what happens when we use the key. Okay. So note that if there would exist such a kind of procedure by Eve, then this trace distance would not be small, because it would give us a way to distinguish the kind of real scenario, namely the one where Eve has kind of made this encoding and then gains some advantage, from this ideal scenario where certainly she's completely uncorrelated and there's no way that she can learn anything. Okay. So it's a very good question. Okay, so this is precisely why kind of this trace distance is kind of well loved by cryptographers, because it means that kind of no matter what we're later going to use with this, do with this key, okay, we're still kind of safe. Okay. Excellent. Okay. So as you might imagine, my next task is going to make this situation ever slightly more complicated. Okay? So let's imagine that we somehow know that Eve's min entropy is bounded. Okay? And we've seen now a few ways how we can know that Eve's min entropy is bounded. Maybe we have some guarantees that she cannot intercept perfectly. Maybe her storage is limited. I don't know. But I want to say, let's just consider the situation where we know that Eve's min entropy will be bounded. It's bigger than something. I don't know. May just call this gamma times n, okay, some fraction of n. So now I want to consider a different situation where, in fact, this channel here to Alice and Bob does not transmit this string perfectly. But instead, whenever Alice tries to send something to Bob, there will be a bit of noise. So there will be some channel here that has the following property. Okay, so whenever I'm going to paint it like this, whenever Alice inputs a 0, in fact, with some probability p error, it will come out as a 1 to Bob. And whenever Alice inputs a 1, okay, and with probability 1 minus p error, it will stay 0. Let me maybe emphasize this. And with probability, like the same probability, if Alice inputs a 1, with some probability it will get flipped, again p error, and with this probability 1 minus p error, it will be transmitted. Actually, is this readable from where you are? No? Okay, good. Let me create some more space. So let me make this kind of box a bit bigger. So let's imagine that whenever Alice tries to send a 0, it will get flipped with some probability to be a 1. So there's some error probability p error. But with probability 1 minus p error, it'll stay a 1. Oops, sorry, stay 0. 0, 1. Okay. And the same happens if we put in a 1. Okay? So if we put in a 1, there will be some probability that the bit will be flipped, which is actually the same, and some probability that the bit will stay the same. Okay. Indeed. So yes, very good. Okay. So like there's someone saying out here, like I know this channel. It is called a binary symmetric channel. Actually, let me make some space here. It's getting kind of messy. And because kind of people are lazy, this is also abbreviated as BSC, standing for binary symmetric channel. And we like to remind ourselves about this error probability. Okay, so I'll write it here. Okay. Actually, if this dries, one cannot read anything anymore on this board, but then you just do this. Okay. And my question to you is, does our protocol still work? Okay. So let me kind of summarize again the protocol that you had proposed, which is like 1, Alice generated this random string. 2, Alice like picked the seed. Yes. And 3. So does our protocol still work? Okay.
Yeah, we just have to inject normal error correction between the steps, and it should be just fine.
Okay. Okay.
Only on the logical bits, on not bits per
Okay.
se.
So there's an excellent suggestion up there, meaning that maybe we should be trying to correct these errors. Okay. So we're kind of Alice is generating the string. She puts every kind of bit on the wire. But of course, what happens is that this binary symmetric channel is going to flip these bits with some probability. Okay. So this means that kind of the bit string that rolls out on Bob's end is not precisely the same thing that we started with. Okay. So like if here I start with like x1 up to xn, then some bits come out, let me call them tilde, which are not necessarily the same because there has been this noise. So note that kind of if we were not to correct any errors here, we would now be in trouble. Because remember, kind of our gold standard, our demand is that Bob must always produce the same key as Alice. Okay? So if we kind of apply this extraction function to kind of a noisy string, which is not the same as the string x that Alice has, then even though Bob knows the seed, he will get a different outcome. In fact, if you think about how two universal hash functions are defined, the probability of a collision was also very small. Okay? So in fact, the probability that the extractor will produce the same outcome on different inputs was in fact deliberately small. Okay. Okay, so we're definitely in trouble if we don't correct any errors.
What does Eve receive? What does Eve receive?
Okay. Okay, so what does Eve receive in the scenario? So I want to kind of work with a scenario now where for some reason, and I hope I've given you some reasons to imagine that scenarios where we might assume that. I want to assume that the only thing that Eve knows, or that we know about Eve, is that somehow we can guarantee that her min entropy about the string x, given what she has, is large. Okay? I don't know, larger than that. So maybe L is some fraction of the n bits, but doesn't matter.
You use traditional coding. Then this problem is currently reliable channel problem.
Okay, so like this, I guess there's two very good suggestions here. Namely, we know something about this. We know how to correct errors in principle. if we did not kind of live in this world of kind of trying to produce a key, and we just wanted to send some information from Alice to Bob, well, we know some tricks for that. Namely, we could apply error correction. Okay. Yes?
Can you send it back to Alice again, if you don't know errors?
Okay. So there's a suggestion here. Maybe we don't need to correct errors, but we maybe send these back to Alice again. Okay.
And then somehow import errors and send back to Bob.
Okay. That's right. I guess this comes back to the question of how we're going to correct these errors. Okay? Like maybe we're going to use some kind of error correcting code, or maybe they're going to talk back and forth. Okay? But in the end, our goal will be basically to communicate. Okay? So in our protocol, we have to add some extra communication, maybe back and forth, or maybe just one way, that in the end will make sure that from this string x tilde we can produce. No? From the string x tilde, we can Bob can reproduce the string x. But note that this does not come for cheap, okay? Like if we're going to kind of do some error correction here, let me just call this error correction, okay, ECC. Then we have now communicated some bits, right? We've kind of communicated something. And let's say that the number of bits that we translate to this error correction step is actually k. Okay? Does this affect our security? Yes?
All of these, there's some probability that Eve learns something about these k bits, and this gains extra information for Eve, so it reduces our security.
Okay, indeed. So there's now a worry, because we're going to send some extra stuff. And this stuff actually has something to do with the string x1 up to xn. Okay? It's certainly not independent, because it somehow must depend on this string, so we can find these errors. Okay. So this means that from these k bits, Eve might now learn something extra. Okay? So Eve is going to kind of collect these error correction bits, and I'm going to call them C. Okay. So if we do this kind of step, like we're going to perform some kind of error correction, then at the end of the day, Eve has her original information E, namely the one that she had initially collected somehow. And now she gains something extra, namely she learns this error correction information C. Okay. So my question to you is now, let's say that we know something about the entropy in the beginning. Okay? We had somehow established that if I had omitted this C, C was not there, then my entropy is L. Okay. So my question to you is now, if I add this C, by how much are we going to reduce this entropy, potentially? Or how much extra information might we kind of give to Eve? Yes? Okay, very good. Dimension C. Okay. So remember that we can always kind of get rid of this by just subtracting the whole size of it. Okay. So what this means is that we can here subtract the dimension of C. Actually, I'm kind of running out of space here a bit. Okay. And so what this means is that our entropy is at least as large as the original entropy L minus the amount of error correction. And I had said these are going to be k bits, so minus k. Okay. It's this k. Okay. Very good. You're like experts at min entropy now. Okay. So I don't have time to kind of discuss explicit error correction methods, because we still want to do a little bit of quantum at the end of this talk. But I want to just ask yourself, because I guess there were some people who know something about error correction. Do you know something about how large this k maybe has to be for a particular error, p error? Does someone know that? Or do you maybe know it?
Depends on the length of the code.
Okay. Of course, it's going to depend on like the number of bits. So I don't have time to talk about this, unfortunately. So let me just maybe tell you the answer. So the number of bits that we have to send is actually equal to what's called the binary entropy of this error probability, okay, if n were very large. Okay. So typically, like, this can only be achieved asymptotically, so typically k is around 1.2 times this binary entropy. So what is this binary entropy? Should I define the binary entropy? Who wants me to define the binary entropy? Yes? Okay, good. So the binary entropy is basically the Shannon entropy of the distribution p error n1 minus p error. Okay, so this binary entropy is minus p error log p error. Okay. Minus this one here. Okay, so minus 1 minus p error log minus p error. Okay. Can you read that? Okay, good. Okay. So note that if you like later go out and you actually build later a quantum crypto system, in fact, so far we haven't done any quantum yet, but let's say that you were going to kind of build some kind of implement the protocol where you send error correction information, of course you should be subtracting the number of bits from the min entropy for this particular code that you're actually going to use. Okay? Like if you kind of implement the protocol, you know how many error correction bits you're going to transmit, because there might be more or less efficient codes, right? So this just, what I'm telling you here is just that there exist codes for which k is roughly one, or error correction procedures, in fact there's both one-way and two-way procedures, that would make k to be equal to 1.2 times this binary entropy. But of course, depending on what method you use precisely, you need to count all the bits that you've actually sent.
Will it give 100% confidence?
Aha, okay. Okay, so there's kind of a good question now, namely that if we're gonna do some error correction, maybe there's some tiny probability that I'm gonna fail, right? So in fact, there will be some kind of tiny probability, if we do this kind of error correction, that maybe we have failed, okay? So that this string is not precisely equal to Alice's string. Okay. So this brings me actually to an important point that I want to make now, is that if we design a scheme, there's going to be all kinds of errors, okay? And there's going to be what we already talked about, and I will call this a security error. Okay. And the security error will be kind of this epsilon here, okay? So we're going to generate a key, but we only know that it's kind of epsilon close in terms of the trace distance to this ideal scenario. So the security error, let me call this epsilon security, is going to say that, well, this key that we're generating, whatever Eve has, okay, so Eve also has a seed, is close to uniform and uncorrelated, using this here, less than epsilon s. So in any kind of actual real-world implementation of a cryptographic protocol, where we might need to correct errors, there's also a error which is called the correctness error. Okay? Which I will call EC. Okay. And you can kind of think that here the probability, in this case it would mean that we wanted the probability that kind of the string that Alice outputs, that this is not equal to the one that Bob outputs, is very small. Okay. And of course, we want to make this as small as possible. Okay. Ideally 0, but maybe we cannot always achieve that. Okay. So when kind of designing a cryptographic system, actually, people usually try to just talk about one epsilon, so they're roughly of the same order. Okay. But in principle, you could also make them different. Okay.
Can we just repeat everything here?
Mm-hmm. Okay, so the question is kind of maybe there's some kind of different kinds of noise. It's not binary symmetric noise, but maybe it's some kind of lossy channel, like erasure noise. So also in the case of erasure noise, one could do some kind of error correction. Okay. Of course, how we're going to do this error correction, we're going to look at the noise and what is the parameter, like the probability here that I get flipped or the probability that I'm lost. Okay. Okay. So unfortunately, I don't have time to delve into the details of kind of how we're going to do this error correction. But in the remaining kind of 20 minutes, I want to talk about quantum key distribution. Okay? Quantum key exchange. So far, there was nothing quantum. There were kind of these magical channels or these magical kind of assumptions that I could make that allowed us that the min entropy is large. Okay. So I want to now make this quantum. Actually, maybe I should have kept this, but let me just write it again afterwards. Can I erase this? The cheat sheet? Do we still need the cheat sheet? Yes.
Students are supposed to copy cheat sheets, so if they haven't copied it now, there's something.
Too late. I guess most of you have a mobile phone, so you can easily produce a copy by taking a picture. I'm actually surprised that none of you have done this yet. When I was teaching in Singapore, there were certain instances in my lecture where everybody pulls out their phone and makes a picture. So the remainder of this lecture, I want to do quantum key distribution. Okay? And quantum key distribution will address us to kind of allow us to address precisely this problem that was brought up by some of you earlier. Namely, like, what about these crazy assumptions? Like, why do I know that Eve can only learn this bit with probability a quarter? Okay? I don't want to make such an assumptions. And we're going to replace these assumptions that we had made, like that she can learn it with probability quarter or that her memory is bounded, by some quantum properties that we're going to exploit to show that the min entropy is large. Okay. So Alice and Bob are still connected by this kind of classical authenticated channel. And in addition, we're now going to give them a quantum channel. So Eve has full access to the quantum channel. She can kind of modify the messages there. She can inject messages. She can try and read the messages. And we're not going to make any assumption anymore. She has an arbitrarily large quantum memory. She can do anything. Okay. In fact, she might have produced this channel. I don't know, Eve has all powers. So the question is kind of, is there something that we can do using kind of properties of qubits or quantum measurements such that we can, in the end, ensure that this min entropy is very large? And to do this, in fact, I want to explain to you kind of a small little game. And I hope that from this game you can then see how we're going to construct a protocol that will do precisely this. And I will call this the guessing game. And this guessing game allows you to actually get a very easy proof, in fact, also later of quantum key distribution. Of course, I'm not going to do this whole proof, but you can read about it here. So I'm writing 2013 because in fact it's a proof that is even partially device independent. I also don't have time to talk about this. But it's a very nice proof of QKD in the sense that it does not use any kind of crazy theorems, it just uses linear algebra. Okay. So if you want to know more about it later, you can read there. Okay. But so what is this proof based on? Okay. It's based on the following idea, that we know something about quantum states, and quantum measurements, and quantum entanglement. Okay. So we know that quantum measurements have some uncertainty. Okay. And you can think that, in fact, one way to think about this uncertainty is also as a guessing game. So I'm Alice now. Okay. And what I'm going to do is I'm going to play the following game with you. I can make two measurements, okay? And I'm going to choose one at random. So either with probability half, I will measure kind of in a standard basis, in the computational basis, or otherwise I measure sigma z. Or with probability half, I'm going to measure in what's called the Hadamard basis, or I measure in sigma x. Okay. So kind of from this, I'll get some measurement outcome, which I will call, I don't know, x1. So there's some choice of basis, okay, which I will call theta. Okay, so here like theta is z, and here theta is x. So I now challenge you to the following game. You can send me any state that you want. Okay. I'm going to make this measurement. I'm going to choose a random measurement. I'm going to make this measurement. I'm going to tell you, because of course I'm at least a little bit fair, what measurements I've made. And you're going to win this game if you can guess my measurement outcome. Okay. So you can think that somewhere, maybe you're Bob. You can send me the state, rho. I'm going to measure it, and I'm actually going to tell you what is this theta. Okay? So you can think that later I give you theta. Actually, let me not paint it like this. So I only give you theta after you've already prepared the state. Okay. And you can produce an outcome, I don't know, x1 Bob. And you're going to win if this is the same as my outcome. What are you going to send to me? Any takers? Aha, okay, very good. It's great. I'm stopped making stripes, otherwise it's okay. So, like, you are quite smart, and basically you're saying, well, you know, if I'm Bob, I'm going to prepare an entangled pair, and I'm going to send 1/2 to Alice. Okay. Note that an EPR pair is kind of entangled in every basis, okay? So, like 0, 0 is the same as, as plus plus. So I'm using plus here and minus to use like 0 plus 1 and 0 minus 1. So these are the eigenstates of sigma x. Okay. So indeed, you will be able to win my game perfectly. Okay. So let's imagine that we kind of make this game yet more complicated. Namely, we're going to introduce also Eve. So Eve and Bob here are actually, you should imagine for the moment, just for the moment, playing against Alice. Okay. Eve can kind of, has control of Bob. She can kind of give him some arbitrary, like she's going to like determine a strategy. They together prepare a state, going to send to Alice. And afterwards, we don't just kind of send theta to Bob, but we send also theta to Eve. Okay, so you can actually imagine that maybe the left half of you is going to be Bob, and the right half of you is going to be Eve. Okay. And now you're kind of playing together in the sense like before, you can decide which state you're going to send me. But in fact, you cannot communicate anymore after the game starts. Okay? So when I tell you theta, I'm going to tell you guys theta. I'm going to tell you guys theta. And without talking to each other, you have to produce an outcome. Okay? So Eve kind of produces xe1. And you're going to win if and only if, well, not only are these kind of outcomes correct, but they're both correct. Okay? So both of them are equal to each other and equal to the outcome that Alice has produced. suggestions? So not that using some suggestions you could win my game perfectly, okay? But we didn't have Eve in the mix yet. So there kind of Bob had prepared half an entangled state and sent it to Alice, and we can win perfectly. Any ideas? Can we do this now here as well? Yes?
Use 0, 0, 0, 3 state.
Okay. 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 So there is a suggestion, which is of course to say, okay, well, we cannot kind of use the EPR pair, we're going to use the GHZ state, for example. Okay. So this is an excellent suggestion, even though I claim, and unfortunately I don't have time to establish this, that in fact this state will not do the trick. Okay. And I will give you some intuition why this is so. Okay. So Susanne's suggestion said that if Alice and Bob are maximally entangled, then Bob can always produce the correct answer, no matter what measurement Alice has been chosen. Okay. So for every measurement of Alice, like X or Z, there exists some measurement that Bob can later do on its entangled state. In fact, in this example, it's also just X and Z, such that he can perfectly guess Alice's outcome. So in fact, the only state that has the property, so one can prove that the only state that has the property that Bob can kind of perfectly predict the outcome of Alice's measurement for both X and Z is precisely the maximally entangled state. So we've seen that kind of we can use the maximally entangled state to kind of perfectly predict what Alice is going to do. But conversely, we also see that if Bob wins this game perfectly, then we know that Alice and Bob have the maximally entangled state. Okay? And I don't have time to prove this, but one can establish this. So in essence, if they win this game perfectly, okay, meaning that this is always true, then in fact, the state that Alice and Bob have is maximally entangled. Okay? It's an EPR pair. Or equivalent to this, in the sense that like it might be rotated on one side, like maybe it's one of the other Bell states, but note that from all of the other Bell states I can locally produce the EPR pair, which is rotating. So we know now that if Alice and Bob kind of produce the same outcome, then we know that they must be maximally entangled. So my question to you is it now possible that Eve can always also produce the same outcome? Yes?
Well, the GHZ state is also maximally entangled, and if Eve does his measurement last knowing theta, he can also win, right?
Okay. So the GHZ state is what is not actually called, so to say, maximally entangled in quantum information, because you will discover, in fact, that if you input the GHZ state, that they can kind of produce the outcome perfectly if Alice measures in the Z basis, okay? Because it's like 0, 0, 0 plus 1, 1, 1. So if all of them measure in the Z basis, then we're in good kind of shape because all of the outcomes will match. But it's slightly more complicated here because I want this to be true also for the Hadamard basis.
But Eve also knows theta, and if he does a measurement last, he doesn't disturb anything.
That's right. So note that kind of the state that they prepare does not depend on theta. Okay, I'm Alice. I'm only going to tell Eve and Bob what this theta is after I've already made my measurement. So they cannot prepare a GHZ state in like plus, 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 minus, minus. And in fact, you will discover that it's not true. Like so for this EPR pair, we know that 0, 0 plus 1, 1 is equal to plus, plus, minus, minus. But this is not true for the GHZ state. Yes?
So if we don't know anything about connection between A and B, then we can use EPR pair between A and E. And then EPR EPR pair between E and B, because Eve is, she tries to read, and she can pretend to be Alice.
Okay, so that's a good point, because like the question is, which qubits are Alice going to measure? Okay, because you were saying, okay, so maybe Alice and Bob have some kind of entangled qubits here, and well, maybe Alice has a second qubit which is also somehow entangled with Eve. Okay. So it's important that in fact I'm not going to allow that. Okay, so the qubit that Alice is going to measure is always going to be the same. Okay, so I'm interested in kind of the correlations between the same qubit between Alice and Eve and the same qubit between Alice and Bob. Okay. So it turns out that kind of a property known as the monogamy of entanglement actually prohibits that A and E are also maximally entangled. Okay. So we know if we were to do such a test, okay, like we just play this game and we see Bob can reproduce the same outcome, then we know that Alice and Bob kind of are maximally entangled. They share something equivalent to an EPR pair. But at this point, we know that by the monogamy of entanglement, in fact, if these here have an EPR pair, in fact, their state at this point would be pure. Okay? So at this point, if we would know this, then in fact, the state rho ABE would be pure. I'm going to call this EPR pair, I don't know, phi, would be pure on Alice and Bob. Okay, so what do I then know about the state of Eve? Indeed, you don't know anything, but because this is pure, we in fact know that Eve for sure cannot be entangled. So I'm claiming now, and I'm not going to prove this, that in fact one can prove the following statement, namely the probability that kind of Bob and Eve win this game in the sense like they can prepare in state, it's get measured by Alice, afterwards we tell them what the basis is and they get to produce an outcome and they win if and only if the outcomes are the same and equal to Alice, that this probability is never larger than this. And it can also be attained. Okay? So there exists a strategy with which they can win this game with probability 85%. Okay. So note that such a strategy is somewhere in the middle. Okay? It's not like maximally entangled between Alice and Bob and Eve is uncorrelated. Okay? It's more complicated. Okay. Very good. So the last thing that I want you to do, in fact, I'm sure you can do it by now, is to now take the protocol that we had constructed earlier, okay, and adapt it to the situation where we have a quantum channel. And kind of going back to your question earlier, like classically we had sent a classical bit string, x1 up to xn. Okay. But what we might do now, having this kind of game in mind, okay, is that the first step of our protocol, instead of sending like x1 up to xn, Alice is going to prepare n EPR pairs. And she's going to send 1/2 to Bob. Okay? So Alice prepares kind of n of them. Like, of course, in actual implementation, you do one after the other. But I'm just going to say she prepares n of them. And she's always going to send the second one to Bob. Now Alice is going to measure, and she's going to make a measurement in one of these bases. Okay, so Alice is going, for each kind of qubit that she has in her possession, she's going to toss a coin and either measure sigma x, or she's going to measure sigma x. And this gives her a string, x1 up to xn. And for convenience sake, I'm going to let Alice remember which kind of basis she's used in each round. And I'm going to kind of record this also as a string. Okay, x1, theta 1 up to theta n. So Alice is going to remember, have I measured x or have I measured z? So Alice sends these qubits across. Do you have any suggestion what Bob might want to do with them? Okay.
And then they communicate the basis.
Okay. So like Alice, yes?
But can Bob also just store them and measure later when he already knows the theta?
Okay. So like there were, let me first kind of say this suggestion. Notice there was a suggestion over there that Bob is going to measure each of them either sigma x or sigma z. And there was a suggestion up there that in fact maybe Bob can just store all of them. Okay. So we want this protocol kind of to be implementable. Okay. So we want to kind of later, maybe I'm going to give a second. We want to construct kind of a scheme where in fact we can implement it. And in fact kind of quantum key distribution has been implemented even commercially already today. But as you probably, like a lot of you know, it's very difficult to store quantum information. Okay? So we want to have a protocol, in fact, where Bob ideally needs no quantum memory at all.
So Eve is powerful, but Bob not.
That's right, yeah. It's kind of unfair, you know. Like Bob has limited abilities, but Eve is all powerful. I'm afraid this is the way of the world, I presume. Yes?
Bob confirms the measurement, and then they share part of the key.
Okay. Okay, so Bob, let me first write it down. Okay, so Bob's going to measure. And because we don't want him to have any memory, okay, we want him to measure immediately, okay? Like a qubit arrives from Alice to Bob, and he doesn't know yet what this basis is, and he's going to measure, okay? What was your question, actually? No? Okay. Okay. Yes?
Could you define quantum channel?
Can I define quantum channel? Okay. So actually, for the purpose of this lecture, I just really want to think about this rather abstractly. Okay. And in fact, I want to, for the moment, assume that there's no noise. Okay. So this is just what's called an identity channel. Like Alice. It's a map from like a qubit to a qubit, which in fact is the identity operation. Like if people implement quantum key distribution, it's usually implemented in optics. And there's also various different encodings that we might use. But we can talk about it in the break if you want. Yes?
If the measurement is set already, you could just get the entangled qubit, measure it, and just then pass the information on to Bob.
I see. Okay, so there's now a kind of big worry here. Okay, like why can Eve not kind of just, I don't know, intercept this kind of entangled pair and measure it herself, and then later kind of also create an entangled pair and pass this on to Bob?
No problem. No problem.
Okay, so indeed, kind of Eve cannot kind of make a copy of this. But there's actually a subtle thing, and I think this is important actually in your question, is like, what are we going to do next? Okay. So in fact, so far, Alice just sent something to Bob and they measured. Okay. But I guess as my game suggests, we want to maybe compare something about these outcomes. Okay. And I will get back to your question because it's very important. Okay. So Bob measures, and in fact, he confirms receipt of all of these qubits. Okay. So what they're going to do now is that Alice is going to tell Bob which basis she's chosen. Okay? So my question kind of that came to you is, why can Alice not just capture this kind of qubit, wait maybe until this kind of basis is announced, okay, measure herself, and kind of, I don't know, learn basically everything, and then kind of have an entangled pair with Bob herself and pretend to be Alice. Okay. So remember the kind of resources that we have in this protocol. Okay. So remember that we have this quantum channel, but we also have this classical authenticated channel. Okay. So in fact, all of this communication, okay, like which basis I'm going to measure in, and that kind of I've received the right thing, is sent over this classical authenticated channel. Okay. So Bob, in fact, at this point, Alice is going to tell Bob, okay, so these were these bases that I have measured in. She's going to use this classical authenticated channel for that. So Eve can read that channel, but she cannot later pretend to be Alice. Like, let's say that Alice, I don't know, Alice makes an EP upper with Eve, Eve makes an EP upper with Bob. Like, she would then have to tell, like, impersonate Alice and also tell Bob some kind of basis measurements. But she cannot do that. Like, she cannot pretend to be Alice in this transmission. So Bob knows for sure that kind of the bases which are announced here actually coming from Alice and not from Eve.
That's assumption. That's assumption.
Yes, okay. So it's an assumption for the moment that this is a classical authenticated channel. We have it already. Okay. Yes?
But Eve does not need to fake anything in the classical channel, only in quantum channel. Like she can do the same measurements which were announced, and send the new prepared qubits in the same basis which was announced, such that Bob would get the correct measurement result.
Okay, so let's think about this. May this be possible or not? Okay. So note that I said here, and I put it in brackets, but actually maybe I should have like made it very large. Okay, that Bob is actually going to confirm receipt of these transmissions. Okay, so Alice is not going to tell him anything about the basis before Bob says, yes, I have gotten all of them and I've measured them. Okay. Because indeed, precisely otherwise, what you're afraid of could actually happen here. Okay, very good. We are already 5 minutes over time, but I presume we erase something here. So since you're discussing this, like, what's next? Okay. Alice has made these EPR pairs. She's measured them randomly. She sent them to Bob. Bob measured them randomly. Bob said, yes, Alice, I've received everything. Alice is going to transmit this basis to Bob. Okay. So what's next? Yes?
Now Bob can tell Alice where he measured in the right basis.
Okay, so very good. So Bob is going to tell Alice kind of when he measured in the right basis. Okay. Does this help them, just to tell when we measured in the same basis? Yes?
It is, because then we can know which subgroup of measurements give a key.
Okay. So note, however, that kind of from the same basis, let's think about our game. Okay, so we want to use this game. So indeed, kind of Alice and Bob will both have the same basis, but there's some check that we want to do. Okay? Yes?
Next, I would have to compare a few of the proper measurements And if then for the same theta they get different measurement results, then it has to be changing the state.
Okay. So indeed, like there's a session. If we look at this game or these properties of this game here, then we want to compare the kind of measurement outcome of Alice and Bob. And we know that if they're measured in the same basis, in fact, then they should be getting the same outcome. Otherwise, something funny is going on. Okay. So of course, we don't want to compare the entire string. Okay. If we want to compare the entire string, Alice would now have to announce all of x1 up to xn. But we still want to make some key of it, okay? So we just want to kind of compare the strings of a subset of the bits. Okay. Some subset of the bits. Okay. So I'm not going to make this very precise here, so I'm just going to say a subset. Okay? And they check whether on the subset they match. Okay? So they check whether all the bits of this subset match. All, and I'm also going to put all in brackets, or rather sufficiently many. I'm going to say more about this later. Match. For the moment, let's actually demand that all of these bits are going to match to make our life a bit simpler. Okay. Otherwise, we just reject, and we're not going to produce any key. Okay. So remember that we wanted to know something about this min entropy. Okay? Namely, we wanted kind of somehow to get ourselves into a situation where we can say something about the min entropy that Eve has about this string. So the point is now that kind of in this kind of little guessing game, I'm claiming that it will tell us something about the min entropy that Eve has, okay, if in fact these tests are successful. So note in this game here, you can think that in fact this game kind of encompasses something about QKD here, because we've created this entanglement, we've kind of checked, and like we've convinced ourselves that they're in the same basis. But note that in this game, in fact, there exists no state, like Alice, Eve, Bob, that has the property such that if these outcomes are going to match, then this will be perfectly the same. Okay? We said that kind of the probability that kind of Eve, kind of corrupting Bob, wins this game, like Eve and Bob win this game, is in fact bounded by 85%. Okay. So this means that if Bob gives the same answer, then in fact Eve cannot give the same answer. Okay? She could only give the same answer with kind of the correct guess with probability 85%. So this may have seemed like a trivial game, but the point is that now that we can use this game to say something about the min entropy that Eve has about X. Yes?
You didn't say anything about probability for Eve. You said it's probability to win the game is maximum for, let's say, for some situation. For example, if you are, I'm like, it's not the most infallible case.
That's right.
What is probability for Eve then to get result?
Okay.
Is it 0?
So let me kind of, okay, like note that in our, like the question is, might this probability for Eve to, in fact, might be even lower than that? Okay. In fact, in the case where this would be an EPR pair, okay, then in fact, what you're saying is correct. Okay. Like in our actual protocol, and I guess I'm going to get to this shortly, where I put this here in brackets, like sufficiently many, okay, we can gain some confidence on this. Okay. We can gain some confidence because remember that like we're also going, like this is some probability that some strategy gives, but we have to test for it in our protocol. Okay. And we cannot be absolutely sure, say that is kind of probability 0 if we just see one sample, right? We have to test this many times. Okay. So we can only get some confidence that the min entropy is large. Okay. I apologize that I'm being a little bit rather rough around the edges here. Okay. But what I wanted to do here is I wanted to give you some intuition why if this check succeeds, then in fact we've established something about the min entropy of X given E. Okay? And so what can we do if kind of the min entropy is large? What will be the next step in our protocol? Yes? Extract, precisely. Okay. So note that kind of in our real protocol, like we know that, So like once we are sure that the min entropy is large, now we can apply our favorite trick and we can extract. Okay. Of course, if we implement quantum key distribution, like all of these brackets and these errors will become important. Okay? Like there will be some error on the channel anyway. So even if there's no Eve, it is actually never going to be the case that all of these bits match, okay? Because there might have been some errors. And so they have to relax this condition to just checking whether sufficiently many of these match. Okay. So I don't have quite time to talk about it, but I mean, you can, for example, look there, which is quite a simple proof. There's also other proofs of QKD. We might also say, well, maybe we want to have some kind of error correction, okay? So we're going to use some of these subsets of bit for testing. These are going to test. Going to give us some confidence about this min entropy. Of course, this is going to depend on how many precisely matched. And the remainder, in practice, also, of course, might have some errors. Okay. So the remainder string that we actually then want to use to produce a key, also called kind of the raw key, the remaining parts of the string, okay, that we're not going to kind of discard from this testing procedure, there we might still have some errors, but we already saw how to deal with this. Namely, we can do some error correction. Okay. That, of course, is going to shrink our min entropy by, like, about, if we have some kind of binary symmetric channel, by roughly 1.2 times the binary entropy of this kind of noise. Okay. So basically, in the end, what we have, and I'm going to call this here X remain. Okay, so these are kind of, actually, I guess, these are the kind of remaining bits. So the final thing that we're going to get is that we have some confidence about these remaining bits of the string given what Eve has. So this is larger than something. And from this, we will have to, again, subtract the error correction information, because in any zero setting, we'll have to do some error correction. There's unfortunately no way around that. Okay? And then we can extract. So I hope that even though we went a little bit over time, we can all enjoy our lunch now. And I hope you kind of understood some of the tools of kind of why quantum key distribution is at all possible. Okay? So kind of we know this kind of very powerful tool of an extraction. And basically what quantum allows us to do there is to make an estimate about this min entropy without having a priori assumptions. Okay? We can kind of learn something that the min entropy is high just by the property kind of uncertainty in the monogamy of entanglement. And there's one last point that I want to make here, is that we've done now actually is even more kind of, so to say, strong than I had initially said. So initially I had said that in fact Alice's and Bob's labs are impenetrable. But note that in this game, in fact, we can even relax this condition by just saying that Alice's lab is impenetrable. Because note that in this game, in fact, there exists no state Alice, Bob, and Eve and measurements that win this game perfectly. So in fact, here we've even allowed Eve to kind of temper even maybe with the measurement inside Bob's lab, and still the key will be secure. Okay. So with this, have a great lunch, and I guess a great rest of the week.